Hi, I'm Xavier Jones, and I'll be presenting my final presentation on the dosimetric evaluation of a modulated intraoperative radiotherapy system, measurement-based and Monte Carlo modeling investigation. My supervisors were Pejman, Gabor, and Marsha. This study involves intraoperative radiotherapy, which is a specialized radiotherapy technique involving delivering a precise, single high dose fraction to a tumor bed after the tumor has been surgically removed. This aims to eliminate any remaining cancer cells within the bed, preventing recursion and improving the tumor control probability. Normal tissue can typically be displaced out of the radiation field or potentially shielded, which combined with the high dose fall-off typical of the sources used, normal tissue complications can be minimized. Intraoperative radiotherapy can be classified depending on the radiation delivery method. Intraoperative electron radiotherapy involves irradiating the exposed tumor bed with high energy electrons, shown here. High dose rate brachytherapy involves using a remote afterloader to irradiate with high dose rate radioisotopes, featured here. Whilst low kV intraoperative radiotherapy, which is the main subject of this study, involves low energy X-rays. Shown here is the Zeiss Intrabeam, which is the low kV device involved in this work. The Zeiss Intrabeam is a low kV intraoperative radiotherapy device. It produces X-rays that are emitted approximately isotropically, with maximum energy of 50 kV. The dose fall-off is approximately characterized by 1 on R cubed, and it's due to this rapid dose fall-off, potential normal tissue complications may be resolved. It also means that unshielded operating rooms can be used for treatment, instead of requiring patient transfer to a conventional bunker. Despite this rapid attenuation, critical structures may still require shielding, which forms a part of this study. The Intrabeam X-ray source essentially acts as a miniaturized linear accelerator. A potential is applied, accelerating electrons produced from the cathode gun here through its accelerator section here, directed by a beam deflector, passing into the probe here. The probe, which is schematics is shown here, is a 10 centimeter long, 3.2 millimeter diameter evacuated tube made of mu metal. At the probe's tip is a 1 micrometer thick hemisphere of gold. The electrons, accelerated with maximum potential of 50 kV, strike this target and produce low-energy Bremsstrahlung X-rays with maximum energy of 50 kV. The X-ray source can be attached to a maneuverable floor stand during delivery, depicted here. Applicators may be placed over the probe to modify the dose distribution produced. These include the commercially available spherical, needle, flat, and surface applicators. Subject to this study are the spherical applicators, which have diameter sizes of 1.5 to 5 centimeters in increments of 0.5 centimeters. Spherical applicators, when inserted into its incision, fill the cavity and adhere to the tumor bed, providing high conformity. These applicators produce isotropic distributions. They consist of polyetheramide, which is a biocompatible thermoplastic. Applicators with diameters less than 3.5 centimeters have an aluminium layer present for the purpose of beam hardening. Monte Carlo simulations are methods of determining numerical solutions to a problem by random simulations. They often attempt to model real-life systems employing the expectation values of random processes. In medical physics, microscopic interactions between particles are modeled based on known average interaction probabilities, or cross-sections. The contribution of each particle can be added up to determine macroscopic behaviors within a volume. Particles originate from a source whose initial energy and direction are pseudo-randomly assigned based on randomly generated numbers weighted by their known energy and momentum probability distributions. Each particle is known as a history. The particles travel the distance randomly assigned based on the medium's linear attenuation coefficient. It is ray traced to its next interaction site, where the type of interaction is randomly chosen, weighted by known cross-sections. The interaction is simulated, which may involve energy deposition, the release of secondary particles, which also need to be tracked, or the scattering of the particle. This process is repeated until either the particle leaves the volume or its energy falls below a threshold whereby its energy is locally deposited. Due to the random nature of Monte Carlo simulations, significant error may be present, proportional to the inverse square root of the number of histories simulated. Therefore, many histories are needed to reduce this error, which may increase computation time. Phase-based storage is a method of alleviating these time constraints and involves storing all attributes of particles leaving a volume interest, which can be used as a source for subsequent simulations sharing the same geometries. Many of the XNRC is one of the multiple Monte Carlo toolkits suitable for radiation dosimetry applications. It models the propagation of photons, electrons, and positrons with kinetic energies between 1 kiloelectron and 10 gigaelectron through homogeneous materials. It includes the X++ library, which is capable of modeling complex geometries and particles. This study is an expansion of work previously performed by Marsha Chin, employing some of the same methods. Marsha aimed to examine the dose characteristics of the Zeiss Intrabeam system through XNRC Monte Carlo simulations and physical measurements. Models of the bare probe, shown here, and the spherical applicators here were produced. Phase spaces generated using Marsha's bare probe model were used in my study, as well as adaptations of her applicator models. Simulations were performed for the bare probe in each size applicator, from which percentage depth dose curves and dose maps, which are displayed here, were produced, as well as energy spectra. Ionization chamber measurements for the bare probe in each applicator in a water tank were performed and PDDs produced. Film measurements of the bare probe and select applicators were also taken in the tank, with PDDs and dose maps also produced, and the dose is shown here. Marsha's methods of film dosimetry were used and adapted into my work. This study involves the dosimetric evaluation of modulated intraoperative radiotherapy system, or MIRT as I've coined, investigated through both Monte Carlo and film dosimetric measurements. MIRT involves spatially varying the intensity of dose delivered during IORT, modifying the dose distribution to improve conformity to the tumor bed and further sparing healthy tissue. This can possibly lead to the provision of patient-specific intraoperative radiotherapy in the future. Applicators will be designed and tested, characterized through Monte Carlo simulations, from which select applicators will be 3D printed. Film dosimetric measurements will be performed in order to validate these simulations. The applicator designs include shielded and different shaped applicators. Dose distribution data such as dose maps, percentage depth dose curves, and percentage different maps between unshielded and unshielded regions of applicator will be produced, as well as energy spectra, in order to characterize each applicator and their distribution. These will be used to draw comparisons between different applicators. These will also be compared to the film measurements that will be taken to validate the MC data. An assumption will be made that if these select applicator models can be considered valid, then the rest of the MC data can be also assumed valid. The applicator models produced in this study are adaptations of the 3.5 centimeter diameter spherical applicator models previously produced by Marsha Chin using the X+ geometry module. This size applicator is studying this work as it's the smallest applicator that without having a layer of aluminium present, which therefore makes it the easiest to 3D print later. An exception is that whilst Marsha's models use polyethylamide as their media, the volcano PLA is used in this case. Shown here is the applicator design consisting of shields, is one applicator design consisting of shields embedded in the applicator head. Multiple models with varying shield variables were produced, indicated in this table here. Shield thicknesses of 0.05, 0.1, 0.5, 1, and 2 milliliters were studied. The distance from the midpoint indicates the distance the shield starts, i.e. this position from the midpoint here, as a fraction of the sphere radius. 2 angles were studied, as well as multiple shield media such as tungsten, tungsten filament, gold, lead, copper, aluminium. The varying shield variables provides a comparison between the dose distributions produced later. Also, applicators with slices replaced with the shield material also produced, indicated here. Again, multiple applicators with varying variables are produced with distances from midpoints of 0 quarters, i.e. starting from the midpoint here, 1 quarter, 2 quarter, 3 quarters. Also, same 2 angles and materials discussed earlier to use. Applicators with an ellipsoid shape head instead of a spherical were produced. The ellipsoids are an approximation employing the ellipse equation indicated here and the X++ cone stack geometry. Using Python code, an approximate ellipsoid using 100 net crossings was produced. The ellipsoid produced in this study had short and long axis dimensions of 1.75 and 3.5 centimeters respectively. An issue with the cone stack geometry occurred whereby geometry errors arose when developing the ellipsoid in XYZ geometry. Hence, the geometry error limit was increased, which can lead to the increased uncertainty that will be presented later on in the results. Ellipsoid applicators with the shielded sections are also produced, indicated here. Again, multiple models were produced with different shield variables. The material is used the same as discussed previously, and distance from the midpoints are now expressed as percentages between the midpoint and the ellipsoid long axis radius. To score the dose, applicators were developed in an XYZ geometry to simulate delivering dose to a water phantom. A 30 centimeter by 20 centimeter by 30 centimeter prism with voxel size 1.6 by 1.6 by 1 millimeter were used, and these small voxel sizes were required in order to accurately determine the steep dose fall-off that would be present. A 3D dose file was outputted by the sim, which records the dose and error in each voxel and can be analyzed by Python script to produce the dose distribution data required, such as dose maps, VDDs, percentage difference maps. To generate energy spectra, phase space analysis is required, and hence phase spaces were produced of photons leaving the shielded region, as this is the area of interest in this study. Particles are scored entering an X-plane, which is positioned to just touch the outer surface of the applicator in the shielded direction. For the ellipsoid applicators, this is obviously in a different position than the spherical. Simulations were performed using this process here, with 32 cores and 125.8 gigabit memory. The PC used is shown here. All simulations are run parallel for 30 cores. A phase space of the bare probe produced by Marsha's models was used as the source. For sims with 3D dose outputs, 10 to the 10 histories were used. At first, 10 to the 9 were used for all the models produced, but as higher quality results were needed for some of the results, a selection of the applicators were taken, and these were simulated at the high histories. For the spectra sims, 10 to the 9 histories was used. The min and max threshold energies for particle reduction for electron and photons, respectively, were 521 and 700 keV, and 1 keV and 200 keV. The electron and photon absorption thresholds were set to 521 and 1 keV, respectively. To 3D print the applicators for physical measurements, accurate dimension measurements were needed. Here is the Sobel edge-detected X-ray of an applicator, which was provided to me by Marsha, from which the measurements could be extracted to produce this schematic diagram in Fusion 360 of the 3.5 centimeter diameter applicator. Using this, an initial spherical model could be produced as a base, and then with modifications could be made to make the other applicators. Although only a selection of applicators were to be 3D printed, all applicator shapes simulated, which I described earlier, in eggs had models produced along with their respective shields. The selection of applicators were taken to be 3D printed using the Bamboo Lab X1 carbon. The bodies were printed using 100% infill volcano PLA, not polyethylamide, which is what the clinical applicators were made of. This GIF shows a shielded ellipsoid applicator being produced. Shields were printed using tungsten filament, consisting of 93.5% by weight tungsten, embedded in PLA in powder form. It uses the same print settings as regular PLA. The shields are printed separately and glued together later. This image depicts all applicators 3D printed for dosimetric measurements. They include a regular unshielded applicator, 3 embedded shielded applicators with shield position 1/2 with thickness 0.5, 1, and 2 millimeters, 1 embedded shield applicator of position 3/4 and thickness 0.5 millimeters, 1 sliced shield applicator of position 3/4, an ellipsoid unshielded applicator, and a shielded ellipsoid applicator with position 50%. For film measurements in a water tank, a film holder was required, whose design was adapted from Marsha's design. It was 3D printed using 93% infill PLA, providing water equivalence, and is shown here. For film measurements, slices were designed with semicircles or semi-ellipses cut into the edge of a 90 by 60 millimeter rectangle, sort of see here. 1 orientation was to be measured for each unshielded applicator, whilst multiple for each shielded applicator were due to the loss of isotropy and symmetry. For the spherical applicators, the orientations were in the shielded direction, the unshielded, and half shielded, unshielded directions, whilst for the shielded ellipsoid, it was just in the shielded and unshielded directions. For each orientation, 3 film slices were produced, leading to a total of 57 films prepared for laser cutting. Gaff-chromic EBT3 film was used in place of the beambox laser cutter, with positioning camera preview indicated here. And this GIF has been showing the laser cutter in action. 3 films were stacked together within the film holder at once and submerged in the Zeiss lead-lined water tank, shown here. For each applicator orientation, care was taken to ensure correct alignment of the applicator relative to the film edge. The front and side of the setup within the tank is shown here, as well as a full view of the setup here. This is the X-ray source here. 50 kV energy setting was used, and a prescription of 2 grays at 10 mm distance from the applicator surface given, leading to each irradiation taking approximately 7 minutes each. Once completed, the films were removed, dried, and left to stabilize for approximately 20 hours. And here's the final film, picture of the final film after irradiation. The films were scanned using Epsilon 12,000 XL scanner with 300 DPI resolution, 48-bit image type settings. The films were scanned, all 3 films were scanned at once, and 3 scans were taken for each set. The red channel of each scan was extracted, all 9 images registered together, and the average image found. 7x7 medium filter was applied. To reduce PDD curves, pixel values along the central X values were extracted. For the spherical applicators, values along lines rotated by plus or minus 5 degrees in intervals of 1 degree were extracted, whilst for the ellipsoid values along the lines shifted plus or minus 5 pixels were taken. The average pixel values were used to produce percentage depth dose curves. As relative comparison is used and the response to the film in the red channel at the energy used is almost stable, film calibration was not required here. Those maps and percentages different maps of unshielded to shielded side of each applicator were also produced from here. Here's the first of the results. This shows the dose maps derived from the Monte Carlo data for each embedded shielded applicator simulated. The maps are taken in the central cross plane of the applicator in the Z plane. Each axis indicates the X and Y distance from the applicator center. Each map is titled with the shield specific variables. The left image shows the dose maps normalized to their own maximum, with percentage depth dose indicated by the color bar. Whilst the right image shows the dose maps normalized to the unshielded applicator maximum dose, providing direct comparisons between each applicator. As the numbers produced are very small, the log of the PD values is taken. These dose maps provide a characterization of the dose distribution provided by each applicator. The top left map shows the unshielded applicator, which visually resembles its expected isotropic pattern. Comparing shield variables, it visually appears that increasing the shield distance beyond 0.5 millimeters has little effect on the dose distribution shown here. Changing the shield position further from the midpoint acts to tighten the gap, which can be seen here. This tightened gap here, which is produced by the shield. In terms of materials, gold, lead, and tungsten appear to provide the best shielding, but for practical purposes, the tungsten filament is likely the best choice. This depicts the dose maps generated from the sliced shield and Monte Carlo data. In terms of shield material, similar conclusions can be drawn as the embedded shields. In terms of position, again, the same conclusions can be drawn, but it also appears that the sliced shields in the same positions as the embedded shields produce similar dose maps results. So here are the 2/4 and 3/4 position, and compared to here, the 1/2 and 3/4 position, they produce quite similar results. As the sliced shields require more material to print, this data seems to indicate that the embedded shields are the favorable design. Here are the ellipsoid dose maps from the Monte Carlo sims. Firstly, visually, the unshielded ellipsoid here dose resembles the unshielded spherical, apart from the added regions of no dose, where the extra regions here where the applicator exists. The ellipsoid applicator can hence provide a dose dampening effect to specific regions, like here, whilst also providing high dose to other regions here, relatively. The shape may also be used to displace tissue away from high dose regions. In terms of shielding variables, similar patterns described earlier are present here, but overall, each of the distributions presented in all of these dose maps provide characterization for each applicator. These are the percentage depth dose curves derived from the Monte Carlo data. The x-axis shows the distance from the applicator surface, whilst the y-axis shows the percentage depth dose. Each plot has multiple applicators plotted alongside other relevant applicators, as well as the unshielded applicator. All applicators are normalized to the unshielded applicator maximum. An inset plot is included to zoom in on the last 5% PDD values. Curves are fitted to each PDD, whose R-squared values are all very close to 1, indicating strong fits. Error bars are displayed, with most maximum errors being below 1%. The highest max error is 3.6014% for the unshielded ellipsoid applicator. The ellipsoid applicators have increased errors likely due to the cone stack issue that I discussed earlier. The first plot shows the effect of changing embedded shield thickness, whilst the second plot shows the same, different shield position. These indicate similar conclusions about the thickness derived earlier. The third plot, shows the effect of embedded shield positions at same thicknesses. Clearly, despite being the same thickness, the 3/4 position has a higher PDD, likely due to increased scatter from having more unshielded regions. The fourth plot shows the effect of shield material, again supporting the conclusions drawn earlier about shield material. The fifth plot indicates the effect of slice shield position, with similar relationships drawn from the embedded shield. However, comparing this to plot 3, it appears slice shields in similar positions to embedded shields provide slightly better shielding. So this is slightly higher than here, which is with the same position. Oh, this is slightly higher than here, sorry. And this is contrary to the, this indicates that the slice shields provide slightly better shielding, which is contrary to the conclusions drawn from the Joe maps earlier, which they were exactly the same. The 6th and 8th plots also show the similar effects of materials that are sliced, and the embedded shields showed earlier for the sliced and ellipsoid applicators respectively, whilst plot 7 shows the effect of position on PDDs for the shielded ellipsoids. Each PDD plot here provides a mean of further characterizing each applicator's dose distributions. These plots are the percentage difference between the unshielded and shielded side of each embedded shielded applicator. The X and Y axes indicate the distance from the applicator center. The color bar indicates the percentage difference. These highlight the spatial effects of shielding, hence providing a further way of characterizing each applicator, as well as giving an indication of the effectiveness of the shielding. In terms of comparisons of shielded variables, nothing new can be drawn from here that hasn't already been explained. These are for the embedded shields. These are for the sliced shields. These are for the ellipsoid shield applicators. Here, the energy spectra for each embedded shield applicator is depicted. The x-axis indicates the energy, whilst the y-axis, the number of photons. Sorry, x-axis energy, y-axis number of photons. On each plot, the shielded spectra is plotted alongside the unshielded. So the shielded is plotted alongside the unshielded, and the average energy of the unshielded spectra is indicated. Oh, sorry, of the shielded spectra is indicated. The mean energy of the unshielded applicator is 31.02 kV. The shielded applicators have higher mean energy due to beam hardening, whereby greater amounts of low energy photons are attenuated, leading to a higher proportion of higher energy photons, shifting the spectra slightly to the right. Shield attenuation effects can also be observed here. These spectra find a way of characterizing each of the applicators, with both attenuation and mean energy effects being discovered. These are the energy spectra for the slice shield applicators, and these are for the ellipsoid spectra. Here, the unshielded mean energy for the ellipsoid is slightly higher, 32.71 kV. Next, these are the film data measurements. The film data was used to verify the Monte Carlo simulations. Here, comparisons between dose maps produced by film and corresponding MC data are displayed. The relative position of the film is displayed on the Monte Carlo map, color-coded. Visually, the film maps appear to closely resemble the Monte Carlo maps, apart from some small outcroppings, which are shown like here, on the edges here. Their presence, however, is not inconsistent with that seen in the log dose maps shown previously, and their presence may be an indication of either the film sensitivity, or they may be due to slight errors in the film positioning during irradiation. Here depicts the rest of these comparisons, again showing similar patterns. The only exception is the ellipsoid applicator, whose 10 to 20% region appears to extend about 1 to 2 centimeters further than it does in the MC map. However, this unshielded region in the next ellipsoid applicator figure does not show this. So here it doesn't have this, it doesn't go to this extent here. And hence, this is likely due to some error in either the film or the scanner. Overall, however, the high correlation between Monte Carlo and film data for each applicator provides support to the verification of the simulations. Depicted here are percentage step dose curves for each applicator, comparing both the film and Monte Carlo data. The unshielded applicator is plotted alongside each shielded applicator, with both film and MC data present. Data is normalized for the unshielded applicator max. Also plotted are the fitted MC curves. Below each graph is a plot of the percentage difference between the film curve and the fitted MC curves for both applicators shown. In terms of film errors, all max errors are below 4%, indicating the reliability of the results. Root mean square error values between the MC and the film curves are also quite low, especially for the spherical applicators, which are all below 0.03%. From the plots, all percent differences are clearly below 4%. For the ellipsoids, however, in the final plot here, the root mean square values are each above 0.11%, which indicates slightly more deviation compared to the spherical, and also reflected in the max percentage difference on the plots being around 14% here. Also visually, the film data doesn't seem to fit the MC data as well either as for the spherical applicators. The high difference is likely due to the low signal available to produce the PDDs, due to the increased distance of the applicator surface from its midpoint. This results in PDDs needing to be derived from regions with more noise prevalent, and it is likely the dose prescription was increased to increase the signal. Similar results produced by the spherical applicators will be found. Overall, however, the relatively high correlation between the Monte Carlo and film data further provides validations of the simulations. Finally, presented here are comparisons between the film and Monte Carlo percentage difference maps. The film's relative position to the MC maps are marked out. Clearly, whilst the patterns produced are the same, the percentage difference falls off too quickly in the dose maps. This is explained by the lack of signal, again, in these outer regions, leading to the doses found here being very low and therefore relatively similar. It's likely that if a larger prescription was given to the film dose, the film maps here would more closely resemble the Monte Carlo maps. Despite these differences, the overall patterns being similar supports the validity of the Monte Carlo simulations, although not as strongly as the data previously discussed. The aim of this study was to design and characterize applicators for modulated intraoperative radiotherapy through dosimetric evaluation. Monte Carlo simulations were performed to generate dose distribution data, which were validated through film measurements. The high correlation between the Monte Carlo and film data provides validation for the sims of the tested applicators, but also an assumption can be drawn from this that all the simulations can be considered valid based on this data. The distribution data generated characterizes each applicator for potential future use, such as in patient-specific MIRT, where applicators may be chosen based on a specific distribution required for the patient. In terms of future work, more applicator designs could be produced, or the development of a treatment planning system using this data may be performed. Study using polyethermide instead of the volcano PLA may also be an option, because this will help transfer this into clinical use. These are some of my acknowledgements to people who helped me throughout my research. So Pejman, Gabor, Marsha, Gavin, Kaylee, Rashid, and the medical physics cohort as a whole. These are just some references for the images used, and thank you. Any questions?
Thanks, Xavier. Very well done. Any questions for Xavier?
I just wanted to ask a question, but I think you answered my question at the end of your presentation. That, of course, when you printed out the ellipsoid ones, and I think the distances used it's too big. So again, my question would be, yeah, what would you do differently if you have the knowledge after you gathered with this kind of measurements? Because this is why we print out something, we measure it, and realized, yes, next time we should start with the slightly different dimensions. But this is how you learn.
Yeah, I would have used just a slightly shorter distance for the long axis of the ellipsoid, because that would have been easier, or potentially using a higher prescription, but that would also mean leaving the film in the water for a bit longer. And we saw when we did that with the longer things that we tried that this would cause film damage in the edges of the film. So that's probably not the best choice.
I just wanted to say something. I've been observing Xavier working on his project so intensely, and he has been working hard, really working hard, and he has achieved so much. I believe he should be congratulated on his achievement. It's great.
Thank you.
Brilliant. Very well done, Xavier. No more questions by the looks of it. So thanks for the presentation.
Thank you.